Alright, now that we know how to write and analyze elemental symbols, let's talk about the periodic table for a little bit. So in 1869, a Russian scientist named Mendeleev excuse me, noticed that certain groups of elements had similar properties. There were groups of elements that behaved similarly, and then there was another group that behaved similarly. They behaved differently from each other, but inside the group, all the elements behave the same way. And he realized that if you put these elements into a line here, so if you just start with the smallest element and just put all the elements in a line, those similar properties reoccurred periodically as you went down the line. And this was really the discovery that he made, because other people had realized before him that certain elements behave similar to one another. So it was widely known that magnesium and calcium, for example, had similar chemistries. But it was just kind of oh, that's interesting. Those two things behave similarly. Okay, moving on. It was really Mendeleev that first put it together that not only are there elements that behave in a similar fashion, but the reoccurrence of these similar properties was a periodic thing as you went through the elements. And so what he did was he took all these elements and he arranged them so that the elements that had similar chemistries were near each other in what was the first periodic table ever created, instead of just being in a line like this. He rearranged them so that the similar elements were close to each other. Doing this, he actually was able to predict the existence of some elements that hadn't even been discovered yet. So he didn't even have, he had no evidence that they were there other than he was expecting there to be 8 elements between this one element and this other element, and people only knew about 7. Saying, well, if there's supposed to be 8 elements here and I only know about 7, there must be an 8th one somewhere that hasn't been discovered yet. And so he was actually able to predict the existence and even the properties of elements that had never even been observed. So this is our modern periodic table. It looks a little bit different than the one that Mendeleev created, partially just because he decided to make his portrait instead of landscape. So he had his lined up this way, essentially, up and down, and then the columns were going in this direction. So I guess for some reason he thought that looked better, but I think we have it this way just because it fits better on our pieces of paper to have it landscape, because you absolutely could arrange it the other way if you wanted to. This periodic table that we have, that we use now, has lots of different ways that you can categorize the elements that are on it. The 3 biggest ways that we categorize elements on the periodic table is we break them into metals, nonmetals, and metalloids. Now, the metals are down here in the bottom left side of the periodic table, which is kind of a bit of a misnomer because they're not really in the corner. They actually make up the majority of the periodic table. I would say, I don't know, what is that, like 2/3 of the elements on the periodic table are metals, at least. The nonmetals are in the top right corner, up here. And then the metalloids, which are kind of in between the two, both in terms of their properties and actually physically in between the two on the table, are right here, this little sliver between the two. The one exception to this, by the way, is hydrogen. It's a little weirdo up here in the corner all by himself. Poor little guy. There is actually an argument to be made that hydrogen should be over here on top of fluorine. And there are sometimes, honestly, sometimes I think that it should be there, and then there's other times when I can see why it's not. It just depends on the situation. With some properties and some of its reactivity, it seems like it should be over here, and then sometimes it seems like it should be over here. So I can see it both ways. Alright, so let's talk about what makes these things different from one another. So you probably have a good idea, even without looking at all these things, because we kind of we're used to dealing with metals in our everyday life, and so we kind of know what some of the just very general properties of metals are. So for example, metals tend to have luster, which is a sciencey way of saying they tend to be shiny. They also tend to be electrically and thermally conductive, which is to say they can conduct electricity, and they also heat up and cool down very easily, which you know very well if you've ever stepped on a piece of metal with your bare feet that's been sitting out in the sun for any amount of time. It gets really hot, really fast. Metals also only form positive ions. So if they share electrons or have electrons taken away from them, that is the only possibility. They can only have electrons taken away. They don't get extra electrons. Nonmetals, on the other hand, sometimes they're solid, sometimes they're liquid, sometimes they're gas at room temperature and pressure. Metals, with the one exception being mercury, are all solids. But nonmetals, they can be pretty much anything, just depending on the element that you're looking at. And they can also be positive or negative when they form ions. They're, in general, much more flexible in the way that they can react, both with other nonmetals and also with metals as well. Metalloids, like I said in the previous slide, they're kind of just in between. They have some properties of metals, and they have some properties that are similar to nonmetals. They're really and truly in between the two. So we have a few examples here of some metals. If you notice, most metals are that kind of grayish silver color. I think the only two exceptions to that are copper and gold. Some people try to make the argument that there's some metals that are kind of bluish in color, and I've seen pictures of those particular metals, and I can see that, but I would make the argument that they're bluish gray. They're bluish silvery color, and so it really still does fall into the same category as most of the other metals. Nonmetals, on the other hand, you can see bromine here. It's a liquid at room temperature. Carbon, sulfur, and phosphorus, all solids at room temperature. The noble gases, which are also nonmetals, are, as the name implies, gases at room temperature. So the nonmetals are just much more interesting in terms of their chemistry, usually. They're much more flexible in the way they can react with things. They have a lot more going on, usually. All right. When we break the periodic table up into smaller groups, other than just those three really big groups, the next most common way to separate the elements is into what we call the main groups. These are also called, well, sometimes they're just referred to as the columns on the periodic table, but usually they're just called the groups. The numbering system that's shown here is actually a slightly older numbering system. This is what I learned when I was in school, which was not all that long ago. But this is what I was taught when I was in school. They have a new numbering system now that doesn't use A and B classifications. So the old system would have like 1B, 2B for the columns down here. But the new system is just 1, 2, 3, just all the way across. And so when you get to here, you're at 13 because there's 10 rows of elements in the middle here. So 13, 14, 15, 16, 17, and 18 is how you finish that out. So you notice it's really not all that different. It's just now we have 13 instead of 3A, 14 instead of 4A. The book that we're using does use this newer numbering system, but I wanted to go ahead and show both of them to you because you will see both of them just depending on where you go. If your book that you have is a few years old, you'll probably have that older numbering system in it. But the main thing to know about these numbering systems is that the reason why we have them in the first place is because everything in a column is going to have similar chemistries, if you remember what I mentioned earlier. So this column, for example, is what we call the halogens, which we'll see in just a second. Everything in this column has a similar chemistry. And so it's just more convenient for us, where if we don't actually care which one of those elements we're talking about, we can just say either the halogens, because that's the name for that column, or we can just reference the column. So we can say, if it's reacting with an element from column 17. It just makes it easier for us when we're thinking about the chemistries that are happening here. So, speaking of the names of these groups, so the main groups, like I mentioned on the previous slide there, are these here. So groups 1, 2, and then we kind of skip over the transition metals here, and then 13 through 18 are what are usually called the main groups. And as far as I'm aware, the reason for that is just because that's where most of the interesting chemistry happens. There's quite a bit of interesting chemistry in transition metals, lanthanides and actinides as well, but most of what we're going to be seeing in this class is going to be from groups 1, 2, and then 13 through 18. Those are where most of the chemistry is going to be happening. Because these are main groups here, because this is where most of the, and actually most of the elements just on the planet are in these groups as well. That might be another reason why they're called the main groups. They have special names for these particular columns here. So everything here in group 1 is called the alkali metals. Everything in group 2 is the alkaline earth metals. All these elements in the middle here are the transition metals. These two columns have special names, but if I'm being perfectly honest, I've never heard someone actually use those names before. At least not as far as I can remember. So I'm not actually entirely sure I'm pronouncing the words correctly, but I believe these are called the pnictogens and the chalcogens. That being said, I've never heard them spoken before. They're not used very often. Usually you would just call it, group 15 and group 16. I don't think I've ever heard someone say, you have a chalcogen from this, I've never heard someone say that. Halogens and noble gases, on the other hand, are used all the time. Those names are used all the time. So the names that I would like you to know are these 5 here. Sorry, it made it seem like I crossed that out. I was trying to underline that. So the alkali metals, alkaline earth metals, transition metals, and then the halogens and noble gases. I would like you to know the names for those columns and be able to connect them to the correct column. The lanthanides and actinides, they are important in their own right. We're not going to really see them at all in this class, except very, very briefly, like we used uranium. Uranium's down here. We used that for our chemical symbol practice, but other than just a very brief mention like that, they're not really going to come up. The lanthanides are super important for certain things, like modern day electronics use a lot of lanthanides, among other things as well, but there's a good bit of lanthanides in those. And the actinides are also super important for certain things, but they also are all radioactive. And so we're not going to come across those very often. Alright, I think we'll go ahead and call it there for this video. In the next one, we're going to predict ionic charges using the periodic table and get into atomic masses as well. So I will see you in the next video.